tutorial, informal tutorial intended to show you how to average data, subtract your data, and merge data from different configurations measured on a single sample. What we have shown here is a measurement series which was done on a glassy carbon, a standard glassy carbon, measured in a Zeus 3. And what we have is we have 4 measurements measured in wax, max, sax, and ESACs, the 4 standard positions that we use in the Zeus 3 and different detector distances, and and different measurement times as well. Then we have a repeat again, so double the data, and then we have measurements of the direct beam without any sample. There's an additional measurement down here that came a little bit later, but this is let's say a typical measurement series, covers a very large range. We can see this goes from about 3.5 inverse angstrom down to about 3 times 10 to the minus 3 before we come into the direct beam. Now, again, for those of you that are unfamiliar with this data that we have here, that's typically the direct beams with no sample. And what we have in here is the measured data from the different configurations. This would be for ESACs with the longest distance. This, let's see, this one here would be for the SACS distance. This one would be for an intermediate distance of about 300 millimeters, what we typically call max. And this would be for wax. Glassy carbon is a pretty strong scatterer. These measurements have been done for, we can see that here, 90 seconds to about 3 minutes. And one can just sort of take a look at this and see that the sample scatters a lot more than the direct beam. And in addition, one can see that these data overlay quite nicely, which is how this system is work as we normalize with the incoming intensity. Now, all of these have different intensities, different configurations, and also different resolutions in them. So that all plays a role in it. But in this case, what we're going to do is to first show you how to get from the 2D to the 1D images that we see in here. The second thing we're going to do is to show you how to subtract a background or the direct beam without a sample from the measurement with the sample. And then finally, we'll show you how to merge all the data together in a way so that you get one final curve that you could then save and bring somewhere else, either analyze within XSACT or bring this somewhere else for analysis. The view that I've done right here shows all the one-dimensional files. You can see down here. The two-dimensional files are, of course, also available in the same directory. Having those at the same time can be a little bit confusing. So typically we'll want to show one of them at a time. The 2D data, or rather the 1D data, is created in real time from the 2D data at the end of the acquisition of the 2D data. This takes all the parameters that the system knows, but we do have the option of, after the fact, taking the 2D files and then redoing the 1D. If the header parameters and the whole system is fine, everything is well calibrated and centering is well known and so on and so forth, then these 1D files that are created on the fly should be good enough. If we have some doubt to the data, we may want to take a look at the 2D data and see whether this data looks reasonable, whether this is the direct beam, these all look nice, and then we see similar data and all of that looks good and nice. So we really have no sort of reason to doubt the data anywhere, and with this data set, I would say we'd be fine to use the just the 1D data from the direct from the real-time measurement. Nevertheless, I did want to take this opportunity to show you how to do one of the most common actions in the 2D data averaging. So let me just show you here. how we could take a 2D image and turn that into a 1D image. Let's take this one here, for example. This is a wax image of a glassy carbon. And what we would want to do is we would want to take a look at the analyze portion of XSACT. We'd go into image operations, and there we would do data reduction, the little icon indicating that we're going to go to a one-dimensional image. So in this case here, we've got input data, and we can just drag this into here and we can run it, and that will generate a one-dimensional curve or a 1D curve for us. That data is also available in a data format here, and we can drag that one around and do other actions with that within XSACT. So that's what we can visualize that as that curve, and we could in principle take what was the 1D curve of that same one, so file 0 1D curve, and throw it in there, and to see. Actually, they are really, very, very similar. Those two measurements as we're in there. So that was a simple thing, and of course they should be the same because they're using the same information. Now down here you have a lot of experimental conditions that you can change if you want to do that. One of the things that is the most common is to actually say, well, since we have the direct beam, why don't we estimate from the data where the center of the image is and use the direct beam for that. If we do that, then let's see here, then we get this curve here. Again, it looks very similar because this is pretty good data. It looks very straightforward, and we can again compare with what we had. And right now we can see there's a slight deviation way up here, right where the direct beam begins to come out. So there's a slight shift in the center of that position as it is estimated from the data. At this stage, if we wanted to take this average data and save it, we can do that. We can save one file. We can also remove it from here if we want. We can edit the files, or we can take a look at it in a larger image where we're sort of having a couple of other tools as we go back into the view schedule. So that was one image. Now, of course, I don't want to go through all of these one by one. So I do have a batch mode up here where I can ask to have all of these put into the data field. Let me just see here. Put those in there. Is that right? Let me take this away there. And this way as well. So let me just do that. Of course, it's not going to allow me to take the 1D data that I was trying to put in. I'm going to have to go to the 2D data and then put that in. So if I wanted to, again, I could do that. That will run all of them through me, a little timer down here through for me, and I will get them over here all overlaid on one curve. And again, if I wanted to, I could bring that into a separate line where I could see these come up in the view mode. So so let me go back to the analyze here and say, in the same way, I can say, well, for each image, please estimate the data from where the direct beam is. And then we see the data coming up there. All of that is good, and we can again translate it into, or put it into the view mode as such. Again, it's possible for us within that analyze to go ahead and grab all of this and save all these images that we have in here as to save the 13 files and have those go somewhere else. So this sort of gives an idea of what you can do with those. I do want to point out that there's a little information up here which gives you some specifics for how this particular operation works. There's documentation that can be pulled up, and it's also possible, if you don't have any data, that you can load example data yourself. So basically this allows us to generate data that is that we can use later on in some other analysis modes or save as such. All right, good. But since this data is essentially the same as the diagram, I'm not going to actually use that data. I'm going to take the data that we had over here and just use that one-dimensional data that is there. All right. I haven't mentioned this before, but I want to show that I do get a little preview window down here before I bring them in. I don't have a lot of control in that preview window, but at least it'll give me some idea of what it is that I'm looking at. So at this stage, we're done with the two-dimensional. We've reduced all our images to one-dimensional averaged images, azimuthally averaged images, and we're ready to consider some of the operations. Now, this data set, as I mentioned, had two sets of equivalent data and then an empty data or data without a sample. So there are two operations that I might want to consider here. One is that I can average. Let's see where we have that averaging the data. Let's say that I have many measurements of the same. Many measurements of the same data that I want to have one combined curve from. So I'm going to grab one of these here and one of these there, and I'm going to generate an average curve from this. All right, that's the average curve on that one. No big deal. And that is what it is. We'll put that into this view right here. We'll go back and do the same for the other ones. Here, there. And delete that and do the same for the next one. There and there. We'll average it. Good, there it is. And we will put it into the view that we just had here, saving it. And we'll do the same for SACS. Sorry, go back to Analyze. SACS. Let me delete this and this. And then we'll drag the SACS over here and here. And we'll average this. And then we'll go to Analyze the view, put it into there. And then we'll take the last one, the XSACT. Put it into here and into here, generate the average, and then put that into view here and here. All right, now we have these, which are the average versions of all of these, and we'll go here to the auto scale function of this. Now, one of the things that I would like to show here is if we just zoom in on this image right there, there's a pretty perfect overlay with everything except right in here. So what we have going on here is that we have a number of measurements with different resolution functions in that same area. And what is most likely happening is that as we get to that curve, those different resolution functions are resulting in a slight reduction of the lowest resolution function at the high point as that's being sort of thrown out into the tails of this. So we can take a look see here, and indeed there is a crossing here where this becomes higher out here. So that looks like that's a resolution function issue. And so at some point we will want to select a portion of the curve that has a good combination of, let's say, high accuracy or low noise, but also has the minimal influence from a resolution function. And one can see again that the sort of resolution function difference here is given by the direct beam. And right here, we're really close to that direct beam. So the resolution function will play a significant role. It will essentially smooth the underlying curve and make some differences in these different curves as we merge them. But in this case, we're pretty lucky that we have 4 sets of data. We've got the wax here. We've got the max that's there. We've got SACS, and we've got XSACT. And so we really only need to take a portion of each of the curves as we intend to merge them. But what we can see is that all of these also have the what's it called, the direct beam components in here, and we really want to subtract the direct beams from this average, from these averaged amounts. So let's go and see what tools we have available for that. So the subtract tool here is the one that we use. Now, do notice that it says subtract buffer. It can be used and is really the only tool for subtracting the direct beam as well. I'm certain that at some point we'll have something that just says subtract direct beam, but for now the subtract buffer works correctly as I'll show here in this case. So the way that it works is it allows you to put in your data, and let's put in our data. Here we'll grab these 4 there. We'll put them in our analyze up here. So that's the data. And then this is the buffer or the sample holder or the empty spot that we want to subtract. And in this case, we're going to grab these 4 down here and subtract those. Now, of course, it's a bit of a question of how is this interpreted as we go into here. Well, there's a little batch mode up here that will allow us to change the way that the interpretation of having 4 and 4 are here. Again, we can look up to here to see if there's anything special, something non-obvious that they would want to say. And what this says is that outside the batch mode, should the data contain multiple files, the operation is performed by following the one-to-one correspondence. So the subtraction here is going to be this one minus this one. That's going to generate one curve. This one minus that one is going to generate another curve. This one minus that one, a third curve, and this one minus that one, a fourth curve. So let's just go ahead and take a look at that. Now, we could just take a look here at the other. So are we going to normalize by sample thickness? And no, we're going to disable that because we could, but we're not going to. In this case, we don't know what the sample thickness is of this classic carbon. And then this down here, keep all values above 0.2. I believe that's pretty irrelevant for the steps that we're just doing right now. So let's just try and do this and see what we get. And that is, in fact, what we get on that curve. Now, if we take a look at that, we recognize the spots, the steps that we had. If we take just a look at the black curve, we can see that the black curve runs up, and then there's some residual stuff that's going around on the beam. So the subtraction looks like it works well right to this point, and then the differences, the slight differences between, let's say, the direct beam, the strong parts of the direct beam, means that this data here in this range for that measurement is not really trustworthy. We have something in here now. Oops. We have that curve in here for max, which goes up to, let me just click on that and see if we can get that highlighted. That was this one, that's that one. It's not really straight to see. We can for ease sake, we can separate them by a factor of 2. So in this case here, we have this one here, which looks nice. We have a better subtraction of the data there, but still the data of the direct beam there, but still it's visibly not, these last 2 points here are visibly not good with that. Then we've got this one here, again, coming up to here, and finally the last one where we begin to see a sort of a rise in the low end of that. So this was just to get those separated. Of course, if we want to have them be where they really should be, they're overlapping. Again, we can see that there's a slight mismatch here right as the resolution function becomes important. But these are now our subtracted data that we can work with, and now we really just need to join these up to create one continuous curve. We've only taken the, let's say, the points that makes the most sense for the measurement. So we're going to go looking again for a module to work with. In this case here, we will want the merging module that's here. This one is a little bit less intuitive, so I'm going to step through it to show you sort of the cases that are possible here. One thing that this does, you get to put 2 data points in there. So let's grab the 0 here, this one, which was the XSACT. We'll put that in as our data 1, and then we'll we'll put in our next one here and try to bring that into, analyze, and merge that as data 2. Now we can view these in here, showing those there, and of course they are representing different Q ranges. Now there's a number of options here, and they're actually important for this case. The one is that let's say the data propagation rules in here. What it's saying is that if we are outside the range of where they're being merged, we're going to take data from one of those sets. Which set should that be? In the low Q, right now it's chosen to be data 1, and in the high Q, it's chosen to be data 2. Well, it should actually be the other way around for us. Data 1, we want to accept the high Q. That's a good one. So we'll say the low Q is data 2 and the high Q is data 1. So that's one choice. All right. The second choice, let's do the sampling should be the finest possible. And then here, a common data range to merge. Now, the default chooses basically everything from one end to the other, at least a very large range that they cover. Now, what we really want to have happen is actually that we use a fairly small area to merge those, and we take the best data that we can. As I was mentioning before, in the data 1 curve, the range right in here can be compromised by the resolution function. A better solution, or data 2, has a higher resolution and therefore is a better representation of the actual data that we have within this area. So we really want to have the merge area be fairly high out here. So let's take a merge area that basically goes from maybe here, which is 0.5, down to maybe 0.4. So let's do 0.4 here to 0.5 as our merge region of those two data sets. And we run that, and that's the merge of those two. We see that it goes all the way from the low end of 1 and all the way up to the other side of this curve. Now, if we'd chosen a larger, let's say that we had chosen something that was, just to illustrate this, was significantly lower, 0.4, and chosen that, what we could see is that it would go down to the 0.4, but below that or above that, it would take the high Q data, which in this case was faulty with the beam stop, the unsubtracted part of the beam stop correction. So we really want to choose a fairly narrow overlap there, and then so we choose those connections there, or those selections there. Now there is one more thing in here as well, and that is a scaling evaluation. We do have the let's say the option to say, well, for some reason these data didn't scale correctly. They should really scale. Resolution function can be one reason why they may not scale. Another reason could be that maybe there were some small differences in sample that we didn't get to correct to, or whatever else. Or we just want to make the curve look nice, which is not recommended, but we do have that option for scaling within an area. So let's say that we wanted to take this overlap here and scale accordingly. So we could do scale between 0.3 and let's say 0.5 again. And if you keep an eye on the curve, you can see there's a slight misalignment in here. I'll do this for saving. This is one set that we'll save here. You can see that there's a slight misalignment in here with that data set that's going on. If we zoom in a bit, we may be able to see that even more. That's the merge area that we have in here. So we're going from one data set and then into another data set over here. So if we go back to the analyze and instead say, well, we'll actually want to merge our data, or sorry, we want to scale our data within that area. Then we run it, and that probably gets to look a little bit better. Let's take that data and compare it to the other one we had in here, compare it to that one. And we see that that data set is scaled ever so slightly to make a better fit to the actual intensities that we had in that area there. So that is really the scaling function being used here, combined with the merging function as well. I really don't like the scaling because I think that the data that we have should overlap, and if they don't overlap in any major way, then there could be a number of other issues, such as subtraction of cosmic background not being done correctly, or other kinds of scaling issues. It could also be an indication that the sample to detector distance is not correctly calibrated, if there are scaling issues. It's there because the intensity actually scales with 1 over the sample to detector distance squared. So it's a fairly sensitive measurement of whether those distances are correct. But in this case, we now have a well, let me run it again. In this case, we now have a data set that is composed of 2 of these. So I'm just going to put that over into a view. And this view that we had before, I'm going to take that out. This view we can keep. I'll go back to my analyze. So now I want to do a merge again, but I want to merge with the data. Just going to take those out so we clean that slate. I want to merge the data that we had in this view here, which is that combined one from the first one. I want to bring that in, and then I want to merge that with my third data, which I had in here, that one there. So I'm going to grab that, bring that in there. I'm going to view both of those, going to decide which area I want to overlap with. In that case, and I'm going to say I want to overlap with something in here. Maybe even something out here. So maybe overlap in this range here, 0.05 to 0.07 there. And I'm not going to rescale in that sense. And now I've got it down to the next amount. I'm going to take this one here and create my new plot with this one. I'm going to go back into my analyze there and there. I don't think I actually need to delete those. Go into there. I'm going to drop that into that one. I'm going to take that one out up there. So now I've got that, and then I'm going to take my last image here, which was in this one here, that one there. I'm going to take it there. I'm going to go there, and then I'm going to choose a region to merge them in. And in this case here, the data is really good and not very noisy down to, let's say, below here. So I'm gonna go and merge this data based on what I see from 0.1 to 0.2 there. And I'm gonna merge that data, and there we go. All right, so at this point in time, I've got my complete data set in here. That is my curve, my composite curve of all of these come into it. And I do still have some residue from an incomplete beam subtraction here. But at this point in stage, or at this point in time, I can leave that. If I wanted to, I could go into analyze, pick a new module, linear transform, bring in my image here into that, and then basically say, I want to have all of this here included. Just want to make a note that if I'm in this window here. It looks like I've got less choices, but I can double click on that and make that a logarithmic curve. Close that, and then I'm into here, and I can still use those selection tools. So here, I'm good. I'm going to take that. I could also multiply or add some background or something and offset to it, but this is the curve that I'll want. And then I'm in my final curve, which looks like this, and in logarithmic like this. And that's it for my curve. Oh, I should say, of course, that here I can again save this file, bring this elsewhere. I could bring it into some analysis tool that would be over here in my picking of a module. With the only thing that I want to show you very, very briefly is on the subtraction, which is something that you'll do probably quite often. Of course, if your data is really intense, then maybe you don't need to subtract it. You just cut the data where you don't need it. But what we did was this sequential mode where this one or this one was subtracted for this one, and this one was subtracted from this one, and so on and so forth. There is another mode. Let's say that you have several data sets that are all taken in the same geometry. In this case, it would be like this one and this one here. And you have one background that fits all of these. That would be this one here, for example. Then you can go into batch mode. And batch mode means that all of these here are going to be processed with this one as a background. So if we do that here, what we see is that we get two sets of data over here. They of course look very similar because they were the same data, but this would, for example, be the way that you would subtract out something, let's say maybe a temperature measurement or some other kind of dynamic where you're sitting and making multiple images within one configuration, and where one direct beam will get you what you need. So with that, I think with that and this final curve here, which was a composite of all of these, I think I will stop the presentation now. And if there are any additional questions, please contact Xenox support and our application scientists for more information. Thank you very much.